Hello again. Do you see the screen now?
Doctor, I have a question.
Yes.
I don't know if you mentioned it أول ساعة بس كرمال exam sorry test 3 متى راح يكون تقريبا؟
Just يعني 2-3 days after the end of classes.
Okay. Okay. Thank you, doctor.
Well, okay. So in this chapter, we will deal with kinetics of particles, which means that you will relate forces to motion, okay, to acceleration. And then from acceleration, we can relate to the velocity and position. So we will introduce Newton's second law of motion, and we will see how to apply it in different types of coordinate systems. Because as we have seen in the previous chapter, we have introduced how to work in rectangular coordinates to get velocity, position, and acceleration, and also in normal and tangential coordinates. So also here in Newton law application, sometimes you will work in rectangular coordinates, sometimes in normal tangential ones. How to know which one to use? It will depend on the given of the problem. Okay. So first, let us introduce Newton's second law of motion. It's one of the most important physical relations, and it will relate the summation of forces acting on the body to the acceleration it's experiencing. And we know that in static part, the main equation was sum of forces equal to 0, while in dynamics, the main relation will be, in case of a particle, of course, sum of forces equal to mass times acceleration of the center of mass g. So this is the main relation we will deal with in this chapter. Now we have another Newton's law of gravitational attraction. This law will give us the attraction force between any two particles. And in particular, this expression is very important for application, for example, in case of satellites or in case of any object. If you want to find the attraction between the object and the Earth, the force of attraction between the object of the Earth is the weight that we use a lot. And in general, we use W equal mg. So G, the value of G, we can get it from the following relation. Because if you apply this formula on the Earth, so this is the Earth, and this is any particle of mass m, okay? So if I consider in this formula, I have the gravitational constant times the mass of the first object times the mass of the second object over r squared represents the distance between the center of the Earth and the center of the particle. Okay, so this is r. So here, if I want to apply this formula on between the mass and the Earth, I will get g times mass of the Earth times mass of the particle over what is r here? R is the radius of the Earth plus the altitude of the point. Okay, so I can replace r by radius Earth plus h squared. Now, in case, if you remember, we say that g equal 9.81, but what is the condition? We say small altitude or small distance separating from the Earth, from the particle to the surface of the Earth. Okay, because if we have very high altitudes, in case of satellite or space mechanics, then h will be very large compared, it will be comparable to the radius of the Earth and larger also. Therefore, we cannot neglect the effect of h in this formula. However, when we are close to the surface of the Earth, and for small elevations of for several meters order, h is negligible compared to radius of the Earth, so I can set it equal to 0. If I set the h equal to 0, so I am close to the surface of the Earth, then GME over radius of the Earth square, this will give me the 9.81 that you usually use, okay? So 9.81 corresponds to the value of G at the Earth's surface. And as I go far from the surface of the Earth, H will increase and then G will decrease. And in case of satellites, which are very far from the surface of the Earth, I can go to weight of 0, okay? Now, Concerning the equation of motion, as we already said, the equation of motion is sum of forces equal ma. And then, in order to apply Newton's law in a problem, the first step will be to draw the free body diagram. The free body diagram is the representation of all forces, external forces, acting on a body. And if I also in dynamics, we can add another diagram, which is the kinetic diagram. The kinetic diagram will represent vector ma, which is the resultant force. So if you do summation of forces, F resultant will be equivalent to vector ma representing the kinetic diagram. So from the free body diagram, the resultant of the forces is vector ma. And in case sum of forces is equal to 0, then the acceleration will be 0, and this is called the static equilibrium. Okay? And in this case, we talk about static equilibrium in case the particle is fixed. We talk about dynamic equilibrium in case the particle has constant velocity. So this is what it is known about by first law of Newton, which governs static sport. While in this chapter we will concentrate on accelerating bodies, so it's the second law of Newton. Now, what is an inertial reference frame? A frame that is having constant velocity measured relative to a fixed frame is called inertial reference frame. So in general, we take one absolute frame that is fixed, it's not moving. And in case we want to write a Newton law in a moving frame, we should pay attention if it's an inertial or non-inertial frame. What do we mean by that? So if we have a moving frame that is moving at constant velocity vector, v constant, so it means that the frame is translating with 0 acceleration, then we can say that it's an inertial frame. This means that we can apply exactly the same law of Newton in it. Sum of forces equals to ma. On the other hand, in case we have an accelerating frame, so let's say you are in a car, the car is accelerating, then inside the car you will experience an additional force which is called inertia force. Okay, so if you are working in a non-inertial frame, which means that the frame is accelerating with respect to the fixed one, then what will be different is that you should add to summation of forces a force is called the inertia force, Fi. And the inertia force is given by minus mass of the particle times the acceleration of the frame, A of frame. Okay, so let's say you are inside a car. This is the car moving. If it's moving at an acceleration A, you will experience inside it a force that is trying to pulling you backward. This is called inertia force. And I should account for inertia forces when I write my equation of Newton inside a relative to a non-inertial frame. While if I write it relative to a fixed frame, I don't have to add anything. I just put the ordinary forces that I have. Okay. Any question on this? Now, how to apply the equation of motion for a system of particles? In case I have several particles in my problem, I know that each particle will be subjected to certain external forces. If I take each particle separately, I can write that it's exposed to forces that are external to the system. Plus, I have the interactions between particles. You know that by action-reaction, each particle will have interaction with the others. But always, action-reactions cancel out when I do the overall summation. Okay? This is why for each particle here, you should take the interaction with external environment and also interaction with other particles in the system. But when you perform the summation for all particles, and when you do the summation over the system, what will happen is that this term will cancel out. because it is the summation of internal forces to the system, and by action reaction, internal forces will be always opposite. So this term will cancel out. This is why we only have to do the summation of external forces. And we deduce that from this relation that for a system of particles, summation of external forces is equal to summation of MIAI, which is the elementary mass of each particle, times the elementary acceleration. Okay? Now, how to deal with this term? What is some MIAI? We will see together that we can replace this term by the total mass times acceleration of g, which is the center of mass. Because if you remember in statics part, we have seen already this relation. If I want to find the center of mass, نحن وقتها شفناها for the center of area, if you remember. So let's say now I want to find the center of mass. By definition, total mass times position of center of mass is equal to summation of mi Ri. This means I should take the position vector for each particle. If I multiply it by the mass, I can get total mass times Rg. نحن بالstatic شفنا, if you remember بالdistributed load, شفنا انه x bar, which is x of g, times total area total, equals to sum of xiai. So it's a very similar relation, but here it's relative to the area, here it's relative to the mass. Okay, so now if you derive mrg equals some mi with respect to time 2 times, yani the first time you derive, you get a relation between velocities. You get mvg equals to some mivi. If you derive a second time, you get a relation between accelerations. So mass times hg equals sum of miai. So here I can replace this term by mag. Okay. Now, concerning the application of Newton's law, as we already mentioned, it can be decomposed. It's a vectorial relation. So sum of forces equal ma is a vectorial relation that can be decomposed into different frames. It depends on the problem. So in case we are working in rectangular coordinates. In rectangular coordinates, I will decompose my acceleration and my forces into 3 components, I, j, k. This was the method we usually use in statics. So here all I have to do is to write 3 scalar equations. Sum of x equals max, sum of y equals may, and sum of z equals to maz. Okay, so this will allow me to solve for 3 unknowns. And of course, once I find the acceleration, in case it's constant, for example, I can use all previous relations developed in chapter 12. Okay, so I should keep in mind to connect the chapters because they always, in majority of problem, I will need to use both to solve my problem. Let us do a small problem to practice about this. The 50-kilogram crate rests on a horizontal plane for which the coefficient of kinetic friction is mu k equals to 0.3. If the crate is subjected to a 400 Newton towing force, determine the velocity of the crate in 3 seconds starting from rest. First, I will introduce what is kinetic friction and static friction. Okay? If you have this box placed on the ground and you are applying on it a force P, okay, this force P will result in 2 components, Px, Py. The x component will try to move the crate horizontally, while the y component will try to lift the box. So it will be able to lift it in case it's higher than the weight. If not, it will not be able to lift the box, and we have also the normal reaction with the ground. Now, in addition to these forces, we have the friction. The friction tends to oppose relative motion between two surfaces. Okay? Now, why we have two types of friction? So friction can be static or can be kinetic. What is the difference between the two? When I talk about static friction, this means that I don't have relative motion at contact level. So here, in case I have static friction in this problem, the box cannot move. Okay? Now, how to know if my friction will be static or dynamic? In such a problem here, since they only gave me kinetic friction, so I know that my force is kinetic, it's not static. But sometimes they gave me mu k and mu s. Mu k is called the coefficient of kinetic friction, while mu s is called coefficient of static friction. So for example here, if they tell me mu k equals 0.3, mu s equals 0.4, and they don't tell me that I have motion, and I should determine if I have motion or not. How to do it? The static friction is characterized by a maximum value. So F static maximum, the maximum possible value that can be reached is equal to mu s times n. Mu s represents the static friction coefficient, while n is the normal between the two surfaces in contact. So this is the normal n. I should calculate n first to know what is the maximum possible static friction. So here, for example, to calculate n, I need to apply my equation along y, my Newton law along y. So I have here the weight, I have the normal, and don't forget on y the projection of p. So I have py also, which is 400 sine 30. So the first relation I can write here is that sum of y, at least here, I can be sure that because they said no, it's moving on in the horizontal plane. I should have a normal reaction. In case I'm not sure if P will lift or not in crate, what can I do? I do an assumption. I say, let us assume the crate is not moving vertically. What is then the condition to not move vertically? N should be higher or equal to 0. Because if you get a negative value of n, this is not physical. This means that no contact between the surfaces, and then in this case, py will be larger than w, and we don't have any more n, and the crate will be lifted upward. And we can have an acceleration upward if py is larger than w. So here I should do an assumption. I should say I assume there is contact between the surface and the crate. So I can make sure of this by calculating n. I should get a positive value. Or maximum equal to 0. If it's equal to 0, yani I am just at the critical case of lifting. So if I increase a little bit my force P, I can lift upward my crate. So here I will start by saying sum of y equals to 0. I have plus Py, which is 400 sine 30. I have also the normal reaction plus n and minus w. The weight here is 500. If you want, I will take G10 to simplify calculation. I consider G equal to 10. So the weight is 500. So minus 500. And you know that sine 30 is 0.5. So this will give me 200. So of course, as you can see, the weight is larger than Py, so I will not be able to lift my crate, and n will be equal to 300. Okay, so I got here n in this problem, n equals 300. And let us say I gave you mu k equals 0.4, I'm sorry, mu s equals 0.4. This will allow you to calculate the maximum possible static friction that can act on the box. So F static maximum is, so if I multiply 300 by 0.4, I will get 120. Okay. Now, in order to not move the crate, I should not exceed a friction of 120. This means what? This means that maximum, Px maximum should be equal to what if I want to have static equilibrium? Px maximum that can be applied before motion is 120. Because as you can see here, F should oppose Px. So higher is P, higher is Px, and higher is the friction. So I can put variable load. I can increase P, then I will move from static to dynamic case. As Px is smaller than 120, this will lead to F smaller than 120 and no motion. Once I exceed Px, so when Px becomes larger than 120, this means that motion will start. Okay? So here, let us verify what is the value of Px. For this, all we have to do is to do 400 cosine 30. And of course, 400 cosine 30 is larger than 120. So it's not possible then to have a static friction because it's exceeding the capacity of static friction. Then we say that since Px is larger than 120, then F will be kinetic. And the expression of kinetic friction is just that it's equal to mu kf. Okay? So just keep in mind the static friction can vary in an interval from 0 to mu Sn, and the maximum value of it is mu Sn, while the kinetic friction can just take one value, which is mu k times n. Okay? Here, since they just gave me mu k, this will will allow me to say that I have motion. Okay, but if they didn't determine that I have motion, I should perform the calculation to make sure that I'm not in a static case. Okay. Now, the second step now, I am interested in finding the velocity of the crate in 3 seconds. And we know that velocity is related to acceleration, and acceleration is related to forces. So my strategy will be to draw the free body diagram as we did, to write the Newton law to get the acceleration, and then from the acceleration we get the velocity. Okay? Let us do the application. So first, as we said, the first step is to draw the free body diagram. As you can see here, we represent all forces acting on your system. It's P, you have the weight, you have the normal, and you have the friction. And here, since it's kinetic friction, you can express kinetic friction function of normal 0.3 times normal. And always friction is opposing the relative motion between the surfaces. So here the crate is moving towards the right relative to the surface. This is why friction will be in the opposite direction. Now, from this free body diagram, I can apply Newton law in 2 directions. In x first, along x, I have acceleration. So I write sum of x equals max. I project forces along x. I have first 400 cosine 30 minus the friction, so minus 0.3n equals to ma. While in y, no motion, so I can write the relation we did together, plus nc minus w plus p sine 30 equal to 0. Here they use G9.81, so they will just have a small difference in value. They got 290.5 instead of 300. In general, in exams, use 10, okay, because it will facilitate calculations for you. So once we find NC, we can replace it back into first relation, and then we can get the acceleration. And since the forces acting on my system are constant, then the acceleration will be constant. And because A is constant, then I can apply the formulas developed in chapter 12 for constant acceleration to get the velocity. So I can just write that the velocity is given by V0 plus A constant times T. And then all I have to do is to replace, since it's starting from rest, V0 is 0. and I replace then A by its value and T by its value to get the velocity in 3 seconds. Okay? Any question on this? Another problem. The baggage truck A has a weight of 3,600 Newton and tows a 2,200 Newton cart B and a 1,300 Newton cart C. For a short time, the driving frictional force developed at the wheels is Fa equals to 160 T, where T is in seconds. If the truck starts from rest, determine its speed in 2 seconds. And what is the horizontal force acting on the coupling between the truck and cart B at this instant? So in this problem, what do we have? We have 3 cars connected together through couplings. So A is connected to B and B is connected to C. Now they are saying that for an initial start, we are accelerating the system. The driving frictional force is developed only at A. يعني هون إذا بدكم مثل بس نقول إنه you have some cars 4-wheel drives يعني the friction will act on 4 wheels. Other cars will have friction only acting on the wheels at the front level. Okay, so here in this problem, driving friction is only acting at A, at wheels of A. Okay, and this friction is given by 160 T. When they say for you driving friction in the problem, this means that it is acting in the direction of motion of the car. And in general, friction is opposing motion. احنا هيك بنعمل عادة. بس you should pay attention, it's opposing motion of what? نحن الفريكشن is at the level of الwheel مش the body of the car. So if you have wheels that are rotating like this, so they will try to push on the ground towards the right. Okay, so how will be friction then? Here friction will be towards the left. So as you can see here, the friction can play a driving role in case of a car because of the wheel rotation. Okay, so due to wheel rotation, you will have interaction between the wheel and the surface, and then by action reaction, the surface will do on the wheel an action, a forward action that will be driving the car, because if I consider the wheel locally, it's opposing motion of this point, but at the level of the car, it's a driving friction. This is why we call it driving friction, because it helps in moving the car forward. Okay. Now, in case I don't have rotation of wheels, يعني if just my wheels are sliding, يعني مثل بس يصير في تصحيح، ساعتها الفريكشن ما بتعود driving force، بتصير resisting force. يعني in this case when إذا بدكم بصير في locking effect، يعني بصير الكار والwheel like one body. Okay. أو لما يكون sliding dominant على rolling, then the friction force will do a resistance to motion, not a driving role. Okay. In general, I specify for you what will be the role of friction. In general, you can learn this in other chapters, but it's not the scope is here, because here we are considering just particles. In order to understand better these issues, we will go to rigid bodies. But in this course, we will limit ourselves in dynamics to particles. Okay, so just know that when they say driving frictional force, so it is in the direction of motion of the car. So this is Fa. Fa is given by 160 T, and they want from me to determine the speed of the system in 2 seconds. So first, if I want to draw the free body diagram, I have Fa. It's the only force along X. Okay, it's the driving force. The other forces are in Y. So I have the weight of A, the weight of B, the weight of C, and of course, the normal reaction. So, but all these forces are in Y. So I don't care about them. They will cancel out in Y, since sum of forces in Y is equal to 0. What is important for me is along x, the equation along x. So if I write the equation along x, what is the system I will take? Since they are all moving together, I will take the whole system. You know why? Because if I choose to take A alone, I am adding a problem. What is the problem I am adding? What is happening here between A and B? So when I take the whole system, this force is internal. But if I do a cut here, this force becomes external. مثل static لما بدكم تلاقوا internal force, what do? You do a cut. Okay? So first, in order to not increase the number of unknowns, هاخد كل السيستم. Then the only force acting on the whole system will be Fa. So if I consider the positive direction towards the left, then I have plus Fa equals to, since I am considering a system of 3 particles, so I should consider the total mass. So it's Ma plus Mb plus Mc times acceleration. So acceleration along x plus times Ax. Okay? So now all I have to do is to replace each mass by its value. Since they gave me the weight, each mass is obtained by dividing by g. So now I can get a x function of time. Why it will be function of time? Since my force is function of time. So as you can see here, I write the relation, I replace my variables, I get a function of time, and therefore, in this case, if I want to find the velocity, I cannot use the equations of constant acceleration. I should perform integration. So I go back to the relation between acceleration and velocity. We know that the differential relation between A and V is A equals to dV by dt. Now, I can do separation of variables, or if you want, you can perform simple integration. You say it is equal to 0.221 t square plus a constant, t square over 2 plus a constant. And to get the constant value, you apply the boundary condition. So this is over 2 plus a constant. To get the constant, we need a boundary condition. Since they said here it's starting from rest, the boundary condition will be at t equals 0, v equals to 0. So if you replace this condition in your equation, your constant will be 0. Okay, so this will allow you to get the general relation of v with respect to time, and then you can replace t by 2 seconds to get the velocity after 2 seconds. So as you can see here, we did separation of variables, and we integrated here from 0 to v and here from 0 to 2. Or you separate variable, or you do integration and you add a constant that you can find from boundary conditions. Both methods are right. Now, the final step in this problem is to find the coupling force between A and B. So as we already talked about, the coupling force is internal if I take the whole system. So to appear this force, I should do a cut between A and B. Then when I perform the cut, I can take or A or I can take B plus C. Both will give me the same result. And if I take B plus C, then the free body diagram will be as follows. I will just have the coupling force acting on it. Why it's not a good idea to take B alone? ليش بدي اخذ B plus C؟ ليش ما باخذ B لحاله مثلا؟
I would need the force between B and C.
Very good. لأنه إذا باخذ B لحاله كمان I should include the internal force in this coupling اللي صارت external because I did a cut here. So بدل ما يكون عندي one unknown هيصير عندي كمان action of C on B. Okay? Which will add to my other unknown. وأنا معي only one equation. So ساعتها بدي أرجع أخذ C لحاله. So I will increase the number of equations I'm using. This is why I will think about the system that would give me the lower number of unknowns. So I take or A alone or B plus C. Okay? Now here they decided to use A. So if I draw the free body diagram on A, I have the friction force acting on A, I have the normal reaction, and I have the coupling force that is resisting motion of A, and the weight, of course. Now, all I have to do is to write my equation along x. Along x, I have the frictional force at 2 seconds, and they are asking for the coupling force at 2 seconds. So all I have to do is to replace t by its value for the friction. So it's 160 times 2 minus t equals to, now always specify your system to know which mass to use. My system now is A. So because my system is A, then of course I will use mass of A when I do sum of forces. So this is only mass of A times acceleration, and the acceleration is the same one I got in the previous step, because I have one acceleration for my system. So AX is equal to AA equals to AB equals to AC. So in this way, I can get the value of my tension. I have one equation, one unknown. Okay? So this problem is to tell you in general ما حيعملوا لكم إياها هن in steps بس بيسألوكم what is the coupling force between A and B. You should know that first I should take the whole system to get the acceleration, then I take A alone to get T. هلا إذا حدا ما انتبه وأخذ دغري A لحال B لحال C لحال, you should write several equations, so you will get 3 equations 3 unknown. يعني إذا بناخد A لحاله B لحال C لحال, يصير عندنا what are the 3 unknowns؟ يصير عندنا ال coupling force T1 بين A و B, ال coupling force T2 بين B و C, وال acceleration. ساعتها you should write 3 equations 3 unknowns. Okay, so by using good techniques, you can reduce the number of equations to write. Any question on this? Okay, thank you. We continue next time. Bye bye.
Bye, Professor.